Again, I'm Abdalwhab, and I'm here to present our work. It's not just my work; it's a teamwork, and we want to show you guys today what we have been doing. And I hope, first of all, I hope you are enjoying the city and enjoying the conference up to now. And let's directly dive into the details. So our focus here is in MIP detection. I guess almost everyone here know what is MIP, but let's just go through why we think it's a special type of detection. So we think it's special because we are focusing on objects that are very small, like valve, like pipe connection, and those are more difficult to detect. And really detecting them would be very useful because it will save a lot of time in reality. We know that this detection is being done manually and it's being done repetitively while the construction is going on. So it means that a lot of time is being wasted in trying to detect them. And if they are detected good, it could save us a lot of time. And if we do want to do it with automation, what we are thinking of is mobile robots that move around the construction site and take pictures or videos. But such dataset will be so realistic to the fact that some of the images will be like this, blurry, not enough light. So it's a very specialized type of detection. And that's why we think it's worth research. Okay, so other works that are related to this work, a couple of people have used the version of YOLO, which is a very famous model for object detection in general, but to make it especially work for example, for workers detection or for large construction equipments like this one. But the difference here is that those objects are large by definition, and usually, like the picture on the left hand side, they are very apparent and they are dominant on the picture. So detecting them or classifying them would be a very easy task. But in our case, smaller objects and more realistic images that are blurry, not enough light condition. Another work that is close to what we are doing is scan to BIM, where they use open vocabulary models to try to recognize pipes and ducts. Again, recognizing pipes and ducts that are by definition very long is an relatively easy task, and you can use some generalized detectors to do that. So how do you usually do object detection? The perfect recipe, or the recipe that is well known, is that you go around, collect your own data sets if you want to perform good, and then you annotate it, you train your model, you test, see how it performs. If it's not good, you go back again, you collect more data, annotate more data, and you go on this loop for a while. However, this loop could be very tedious and time-consuming, cost-consuming. And the question here is, can we do better? To answer that, if we look at the problem of open vocabulary detection, which is, if we want to understand it roughly, let's say if I told you, if you have never seen an okapi before, and I told you what is okapi, and okapi is an animal that has a giraffe-like head and legs that looks like a zebra. And even if you haven't seen it, for most of us humans, we have this ability that we can, from description, we can try to understand, we can reason, and we can detect those new objects that we have never seen. And that's what we call open vocabulary detection, to try to detect a class or object type that you have never seen, but you know some description of it. Does that sound familiar for people who use ChatGPT or, generally speaking, VLM-like applications? Now they have good reasoning about images. They can tell you stuff about what is going on in the image. And the question is, are they ready to do this? Let me try to see if I can quickly remove this. So are they ready to do this? And this is what we want to answer is this research. Basically speaking, the main contribution of this work is to evaluate real world, is to introduce a new real world data set, because a couple of the data sets that you will find online are less realistic because the objects are well posed. It feels like someone standing and took the picture, like the picture of the crane or the moving vehicle that I show. At the same time, some of the pictures will be blurry if you are working in a factory or active construction site. And we want also another contribution is to evaluate open vocabulary generally, but specifically for MIP detection, which is more specialized domain. And we want to see the real world applicability of such solutions to be used. For the methods, we started by collecting our own data sets we think is one of the main contribution. And we use the robot that you can see on the left side of the picture of the image. And it was equipped by a couple of sensors, but we mainly focused on the images. And we teleoperated the robot in an active construction site, collected around 9,000 images. We annotated it with 14,000 bounding boxes for 10 classes. That's what we focus on. And for the methodology, we want to compare open vocabulary with custom training, because what people do is you train your own model. So we took off-the-shelf pre-trained models that has the claim of doing open vocabulary models, like grounded SAM2 that the lady before me mentioned, and grounding Dino and detect. And we took them off-the-shelf pre-trained, directly evaluated on our testing dataset. And at the same time, we took something well-known like YOLO. The latest version at that time was 11. We took the smallest one, Nano, retrained, and then fine-tuned in our dataset to see how it will perform. And to be fair, both of them were evaluated on the destiny split of the data. And that's roughly the results. So we here report the F1 score, but if you go to the paper, you'll find more matrices. But the gap is huge. We can see that YOLO is able to do 90% roughly detection accuracy with intersection of over union of 0.5, which is acceptable range, where all those models, we can say roughly they failed hugely to do even simple detections. And even for classes where they scored 0, YOLO was still performing good. And if we look at the confusion matrix normalized version of it, we can see that in roughly 90% of the time, the model is able to detect a boiler, for example, as a boiler, cable tray as a cable tray. And in rare cases, it fails. And the failure usually is in the background, where, as I said, sometimes even with a small percentage, but sometimes in the background, there could be an object where the model will think there is no object, or there is a background, but the model says there is an object. And in fact, when we took this further and analyzed an example of the pictures that the model produced at detection, we found that, in fact, sometimes the labeler, the human labeler, was making a mistake. There is actually an object in the background. The human did not see it, but the model that is fine-tuned can see it. And in one case, a byte fit in only one class is misclassified as another class, which is the case of byte fitting with a very small percentage. And it can go up to 100% accuracy or as bad as 89, which is still very acceptable detection. And those are examples of the detections produced by the system. And we are showing this to show how difficult the images could be. It could be as blurry as the one in the middle, and the objects could be as small as a bulb that almost many of us cannot even see. And to take it further, we wanted to understand the real-world applicability of such model to be deployed on a real robot going around to real-time detection. And to answer that, we started by comparing the most important factor, which is the memory footprint of the model itself, as measured by the number of parameters. And we found out that GSAM2 is 350 times larger than YOLO 11, and it goes roughly the same for grounding Dino and detect with 67 times larger and 63 times larger. So for now, it's not really deployable in a reasonable, let's say, robot going around. So to take it further, we also wanted to see the inference time. So we took YOLO 11, we deployed on NVIDIA Jetson Orion, which is a typical processing unit in a normal robot. And we see how it performs with that. And it was able to do 23 frames per second, which is very acceptable for real-time application. And as discussion, we need to stress the point that YOLO fine-tuned with the fact that it's a very lightweight model, it can detect even difficult classes and less represented classes on the dataset. The gap between the two is still huge because mainly those models are trained on generic datasets, so they don't understand all about domains that are specific. And in conclusion, we think this gap needs to be cost shrinked, and many research need to be done to do that. One direction could be custom construction related prompt, where we just enhance the text that we input in. We don't expect it to give a huge enhancement. But the other direction is to build a very specialized large data set to fine tune those generic models. those are the list of references. And with that, I say thank you very much for your time. If you have any questions, please go ahead.